Okay, this is exercise 4B, 2-unit, just some Cambridge worksheets and solutions, velocity and acceleration as derivatives. In the first question, you had to find the functions if x equals e to the negative 4t, differentiate, finding the functions for v and a, quite simple there, fairly straightforward. Explaining why x, v, or acceleration can never change sign. I mean, if you can, there are a few ways to do it. Look, you should really know the shape of the curves. For example, this curve here is x equals e to the negative 4t. It's an exponential curve with a negative power there. The normal e to the 4t would look like this. This is e to the negative 4t. You can see that x is always greater than 0, therefore it never changes sign. Okay, and you could do a quick sketch if you wanted to. The equation for velocity is this one. Velocity equals negative 4e to the negative 4t. Basically, it's the reflection of this top curve in the x-axis, but also each term, each y value here is also, or x value I suppose, because it's x equals e to the negative 4t. Each value is multiplied by a factor of 4. So where we've got 1 there, we've got negative 4 here. Negative meaning it's reflected in the x-axis, and the 4 affecting the slope, making it steeper, and the intercept would be there at negative 4. So we can see that also v is less than 0 for all t, therefore it never changes sign. X is greater than 0 for all t, therefore it never changes. And a quick sketch for A, acceleration equals 16 e to the negative 4t would look like this, cutting through at 16. Again, A is greater than 0 for all t, and therefore A never changes its sign. So therefore you'd be saying that A is positive, V is negative, X is positive. Part B, these are fairly, again, straightforward. Where is the particle initially? Initially is when t equals 0, and eventually is when is as t approaches infinity. Now, initially is when t equals 0, so where is the particle? They're asking the position, so x. When t is 0, x is 1. You can just put it in here. It's x is e to the negative 4 times 0, e to the 0 is 1. Eventually, for large values of t. Now, of course, actually, we can never have, with these graphs, just coming back to them, these parts of the graphs don't exist because time can't be negative, same here, and same there. So really, it's just these portions of the graph that are applicable to the question, because you can't have negative time, okay? Now, as t approaches infinity, we can see what's happening here. As t gets very large, I mean, if you can't draw the curve, you could always substitute a large value of t here, like 100 or something, and what you'll find is that you'll get a very small value close to 0. Sorry, you can't see what I'm doing. Just make that a bit bigger, and I'll move this question up. So, as t approaches infinity, you could put a big value of t here, like 100, and you would find that you get a very small positive value. So x approaches 0. We can also see it here as t gets large, x approaches 0. So that's where the particle's position, that's where the particle is initially and eventually. And then it asks, what are the particles' velocity and acceleration initially and eventually? Well, initially, for part C, when t equals 0, v equals, now we can even see it from this graph, or even we can see that it's at, when t equals 0, the velocity is negative 4. Remember, I should have drawn two separate graphs here, but I've just put them on the one. Should never really do that. But when t is 0, velocity is negative 4 e to the 0, which is negative 4 units per second, or whatever it might be, what the units are. And eventually, as t approaches infinity, we can see what happens to v. It approaches 0 as well. V approaches 0. And again, when t equals 0, acceleration, I mean, you can put it into the equation at 16 e to the 0, which is 16, or just read it off there. And also as t approaches infinity, that means eventually the acceleration approaches 0. You can substitute a large value into this equation here, Or, sorry, you can't see what I've done again, or you can just see what's happening to that graph there. That's question 7. Okay, we've got a cricket ball thrown vertically upwards, and this is its height in meters at time t seconds, given by x equals 20t minus 5t squared. You have to find the velocity and acceleration as functions of t and show that the ball's always accelerating downwards. So just differentiating, you get v is 20 minus 10t, units will be meters per second, and acceleration is negative 10 meters per second. So therefore, acceleration is less than 0 for all t, because the acceleration is just a constant. It's not a function of t. And you're supposed to sketch graphs of x, v, and acceleration against t. Your first curve, that's just a concave down parabola. If you factorize it, you'll be able to get the intercepts, the t-intercepts. And therefore, if you put it equal to 0, x equals 0, you'll get that your intercepts are at 0 and at 4. And so therefore the maximum will be, actually, and it just starts at 0, so don't have it starting earlier, and it stops at 4. And you've got your maximum point there. Okay, you might want to put what that maximum is. 20 times 2 is 40 minus 5 times 4, 40 minus 20, the maximum's 20. Okay, that now your velocity versus time graph, you can see that it's y-intercept's 20 and it's got a negative gradient. I mean, you can just substitute some points. So when t is 0, v is 20. When t is 1, v is 1. V is 10, sorry. And when t is 2, you'll get v is 0. So it's a straight line graph. And the scale here doesn't have to equal the scale there, as long as the scale up here is uniform. And that scale's uniform. So this is the graph of velocity versus t. And the graph of acceleration versus time is just a, acceleration is always equal, I'll make that the t-axis there. And acceleration is negative t. So it's just a straight line at negative t, the acceleration curve. Now the speed at which the ball was thrown is part B. These are relatively straightforward. It's just when t equals 0, find v. It's 20 minus 0, which is 20 meters per second. But you know, you can just read that off the graph initially. The ball was thrown with a velocity of 20 meters per second. When does the particle return to the ground? Again, you can see that from the graph. Particle returns to the ground at time equals 4 seconds. But you can, if you want to formally do it, but you've already solved it here. So therefore, you've already put 0 equal to x. X is 0 and found the values of t. So when t equals 4, it returns to the ground. And show that the speed is equal to the initial speed. So when t is 4, you want to find out the speed. You're just going to notice a little discrepancy here. So when t is 4, we get velocity is 20 minus 10 times 4, which is 20 minus 40, which is negative 20 meters per second. Now that's just traveling at 20 meters per second in the negative direction. So what I haven't done here is if you look at the graphs, the particle is in the air for 4 seconds. So this should have been continued on for 4 seconds. And the velocity down here, sorry, it's not really to scale, but this will be at negative 20. Okay. So, sorry, this is not really to scale. Okay. It should have been a bit lower, and this is my acceleration there, that other graph. So you've got to make sure that your velocity curve is for the duration of the motion of the ball. Okay. So show that the speed, so therefore it travels at 20 meters per second to the left, down. Because remember, when the particle's been thrown upwards, it's positive velocity, and when the particle comes back down, it's negative velocity. So therefore, which equals initial speed. Remember, velocity has direction, and you put the -20 meaning downwards, but speed is just the magnitude of the velocity, not the direction. D, find the maximum height above the ground. We can see that from this graph. Maximum height's 20 meters, time to reach it is 2 seconds, but you can go when you can differentiate if you want, but we can just see it from the graph that maximum height's 20 meters at 2 seconds. So maximum height is 20 meters at t equals 2 seconds. But the other way to do it is to maximize the displacement, find the maximum there of the displacement. So you do the first derivative, which is dx dt is 20 minus 10t, or you can do the following. Dx dt is, which is the velocity, is 20 minus 10t. If you put it equal to 0, you'll get that t is 2. You know that acceleration is always negative. So this is a stationary point at t is 2, concave down, therefore you've got a maximum at t equals 2, okay? But you can see it from the graph. Okay, I'm just going to move this question sheet upwards. And the last question says to find the acceleration at the top of the flight. And it says to explain why the acceleration can be non-zero when the ball is stationary. Now, for example, let's say this is time is 2 here. We know the acceleration is a constant -10 meters per second. Acceleration at the top of the flight is still -10. So acceleration equals -10 meters per second when time is 2 seconds. And acceleration, the acceleration is still negative, even though the ball has stopped. This is because at t equals 2 seconds, the ball is at its maximum height. So the velocity is positive, and you can see here by the gradient, velocity is positive. Then here we've got a stationary point, velocity is negative, and then again the velocity down here, velocity is 0, and then velocity is negative. So acceleration is negative because but the ball has only stopped momentarily there because as velocity is positive when ball is going up, when ball is going upwards, or is traveling upwards, and velocity is negative when the ball is going downwards. Now, at that very moment at the top, the velocity is changing, so therefore that's why there is acceleration. So at the top of the flight, velocity is still changing, and that is why the acceleration is not 0, okay? Now in question 12, it says a particle is moving horizontally so that its displacement x meters to the right of the origin at time t seconds is given by this graph here. It says in the first 10 seconds, what is the maximum distance from the origin and when does it occur? Well, at this point here where I am, time 0, you're at the origin. At this time here, which is about 1 second, we're 4 meters to the right of the origin. Here we're 8 meters to the right of the origin, that's at 3 seconds. Here we're 4 meters to the right of the origin, that's at 6 seconds. Here we're back at the origin at 9 seconds, and 10 seconds would be just about here. We're probably about 1 meter to the right of the origin. So the maximum distance from the origin would be 8 meters. So for part A, maximum distance is 8 meters, and it is when time equals 3 seconds. Part B, it says by examining the gradient. When is the particle stationary? Particle is stationary, so it's stationary when velocity is 0. Now velocity happens to be dx dt, which is 0, which is the gradient of this original curve, and the gradient is 0 at time equals 3 seconds. When is the particle moving to the right? So the particle is moving to the right when the velocity is positive, when velocity is greater than 0. Now that happens to be the gradient of the curve. Now the gradient here is positive between 0 and 3 seconds, and the gradient is positive from 9 seconds onwards. So it's moving to the right when the velocity is greater than 0. In other words, when your gradient is greater than 0, where you've got a positive gradient, and that's from 0 through to 3 seconds, and for t greater than 9 seconds. And that was part 1, this is part 2. Now part 3 says, just make that a bit bigger. When is the particle moving to the left? Well, you're moving to the left when v is less than 0. In other words, the gradient of the curve is negative. Negative gradient between 3 here, between 3 and 9 seconds. Okay. Next one, part C. When does the particle return to the origin? What is its velocity then? And in which direction is it accelerating? So here the particle starts at the origin. Here it's 8 meters away from the origin. Back here it returns to the origin. So particle returns to the origin at t equals 9 seconds, or when t equals 9 seconds. And what is its velocity then? Well, if you look at t equals 9, that looks like a minimum turning point. If you look at the gradient, remember velocity equals the gradient of the x curve. In other words, it's equal to dx dt, but it actually equals 0 at this time. Gradient of tangent to curve at t equals 9 is 0. So therefore, its velocity is 0. In other words, it stopped moving at t equals 9 seconds. And in which direction is it accelerating? Now, acceleration, if this is an x graph, acceleration is the second derivative. So from 0 seconds to about 6 seconds, the curve is concave down. And then from 6 seconds all the way up to a bit over 12 seconds here, the curve is concave up. So for acceleration, it refers to concavity of the curve, because concavity is the second derivative. And if you look at x, v, and a is the second derivative of your displacement. So acceleration is less than 0. It's not. It's greater than 0. It's concave up. Acceleration is greater than 0 when t equals 9, because the curve is concave up, as the curve of x is concave up. Okay, so therefore it's accelerating to the left. Accelerating to the left. So at t equals 9 seconds, the particle is back at the origin. It's not moving. Okay, and it's accelerating to the left. In other words, it's going to start moving to the left. Okay. Now for part E. It's here, accelerating to the left when t equals 9. Okay, now for part D, it says when its acceleration is 0. So if we go back and look at the curve, we've got concave down, which means second derivative less than 0. So from t going from 0 to 6, acceleration is 0. And then from t being greater than 6 up to, say, about 12, say from 6 to 12, acceleration is positive, because it's concave up when from t equals 6 to 12, and it's concave down from t equals 0 to 6. Therefore, at t equals 6, you've got an inflection. And so therefore acceleration is 0. So when is the acceleration 0? It's at t equals 6 seconds. Where is it then? So its position, so at t equals 6, x is 4, positive 4, therefore it's 4 meters to the right of the origin. And it says, and in what direction is it moving at t equals 6 seconds? Well, at t equals 6 seconds, velocity is negative because the gradient of the curve is negative, because gradient of curve is less than 0. Therefore, the particle is traveling to the left. Okay, now for question E. Okay, it says by examining the concavity, find the time when acceleration is negative. We've already done that in part D. So acceleration is negative from t is 0 to 6, but not including 0 to 6. That's when it's concave down, because the curve is concave down. Okay, and for part F, about what time is the displacement velocity, at about what time is displacement about the same as t equals 2? So if I look at t equals 2, which is about here, the displacement's about there. Okay, so at this point here, which I think, if we go t equals 2 about here, I think that's the same as about t equals 4. So displacement is at t equals 2 is approximately equal to displacement at t equals 4 and t equals, so if we're looking at this point at t equals 2, displacement's about there, about the same as t equals maybe 4.5 seconds, and same as displacement around here, which is about t equals 12 seconds. Okay. And when is the velocity the same as t equals 2? So at t equals 2, velocity at t equals 2 is, we can see it's positive, okay, and is approximately equal to velocity at, now we need to get a gradient here. I'm going to go at t equals 2, the gradient's about that. I'm looking for the same slope. I think it's about here at about t equals 10 maybe. So the velocity at t equals 2, you have to look at the tangent to the curve, which might be like this, is about the same as the velocity about here at t equals 10 seconds, because those gradients that I've just drawn out there are about the same. Okay, and that's F. And now for G, sketch roughly the graphs of V, and velocity is the derivative of the displacement curve. So one sec. The derivative of the displacement curve. So here at x equals 3, the displacement's 8. The gradient's 0, and at t equals 3, the displacement's 0, because the gradient here is 0. T equals 9, the velocity is 0. T equals 3, the velocity is 0. T equals 9, the velocity is 0, because the gradients are 0. So we've got that. Now, positive velocity, gradient of curve is positive from 0 to 3. So we've got positive velocity, and also the gradient steepest here, and then it's narrowest there. So it looked like this. And then the gradient, we've got negative velocity from 3 to 9, but at time equals 6 seconds, you've got the maximum velocity. So you'll have, but it's in the negative direction. So therefore that'll be the steepest value, the biggest value of velocity, but as a negative, and then it comes back up. And then from here, we've got positive velocity, okay? So this is a rough sketch of velocity versus time. And for acceleration, remember that's the derivative of the velocity curve here. We've got negative gradients, negative gradient here, 0 gradients, positive. So at time equals 6 seconds, we've got 0 acceleration. We've got negative acceleration from 0 to 6 seconds and positive acceleration from 6 to, I think this goes up to 12 seconds. And it will be a straight line, because if you look at that curve, it's like a parabola, like an x squared graph. If you differentiate it, you will get an x, like like y equals x type curve, which will be a straight line. So therefore this is the sketch of the acceleration curve versus time. 13, x equals 4 cos pi on 4t. It says a particle is moving according to that equation in units of meters and seconds. You have to find velocity by differentiating. Now if you differentiate cos, you get negative sine, and we need to differentiate the pi on 4t as well, and we get pi on 4. So therefore velocity is negative 4 pi on 4, which is negative pi. So it's negative pi sine pi on 4. That's what the velocity is. Now acceleration is the derivative of that curve, which is negative pi times, now differentiate sine, you get cos. So we get cos pi on 4 times, sorry, that's a t. We get cos pi on 4t times the derivative of pi on 4t, which is pi on 4. And so therefore the acceleration is negative pi squared on 4 cos pi on 4t. Okay, it says to find v and a, which we've done, and sketch the graphs of x, v, and a against t for the first 8. Okay, firstly sketching the displacement. The amplitude of the curve is 4. It's a cos curve, so it looks like this. And the period is 2 pi divided by, sorry, I'm just off screen there. It's 2 pi divided by the coefficient of that t, which is pi on 4. So it's 2 pi divided by pi on 4, which is 2 pi times 4 on pi, which is pi on, so 2 pi times 4, which is 8, sorry. So it's 8. So 2 pi times 4 on pi is 8. So therefore the period is 8 seconds. So therefore this here is 8 seconds, this is 4 seconds, that's 6, and that's 2, okay? So that's your sketch of your displacement versus time for the first 8 seconds. Now for the velocity. Now the amplitude is pi. Now pi is in terms of 3.14. So this is pi as in terms of 3.14, negative 3.14. Again, the period is the same, it's 8 seconds, and this is a negative, you can see it's a negative sine curve. So sine curve goes like that, our curves will go like this. This is 8 seconds, that's 4, 2, and 6 seconds. So that's velocity is negative pi sine pi on 4t. And that's your displacement curve, x equals 4 cos pi on 4t. Now for acceleration graph, that's velocity. Acceleration is a cos curve. The amplitude is pi squared on 4. Pi squared on 4, but it's a negative cos curve. This is a negative here. So instead of going like that, it starts from here and goes like this. Again, we've got 8 seconds. So this is 4, 2, and 6. Okay, and the amplitude's pi squared on 4. Okay, so that's part A. Says, what are the particles' maximum displacement, velocity, and acceleration, and when do they occur? During the first 4 seconds. So maximum displacement, and you can just read these off the graph. When time is, so here's the maximum displacement of 4, here -4 and 4. But this -4 means it's just 4 meters to the left. So actually that's maximum distance from the origin. This is maximum displacement because it's +4. So the maximum displacement is when t equals 0 and t equals 8, and it's 4 meters. 4 meters. And it's to the right of the origin, or wherever it's starting from, okay? But this is a maximum distance from the origin, 4 meters to the left, but displacement has to be, the positive is the maximum and the -4 would be the, I suppose, the minimum, okay? Okay, actually, yeah, well, it's the furthest distance away, but to the left of the origin. This is the furthest distance away, but to the right of the origin, okay? And the maximum velocity, if we look at the velocity curve, is at, again, the values here pi, but that's positive pi meters per second. So maximum velocity is pi meters per second at time equals 6. This speed here at time equals 2, it's the same speed, but it's traveling to the left, okay? And the maximum acceleration, so maximum acceleration is at t equals 4 seconds, and it's a equals pi squared on 4 meters per second. Okay, this is a maximum acceleration, but it's in the negative direction, okay? And same with this one. I suggest you need to take into account the, not just the magnitude, but the sign. Okay, now for the next question, part C, it says how far does the particle travel in the first 20 seconds? Now, if we look at the graph, actually I'm going to draw it down here. So this is what we've got, 8 seconds there, -4 and 4 meters, okay? And that's time. So in the first 8, so initially the particle is 4 meters to the right of the origin, then it ends up 4 meters to the left of the origin after 4 seconds. So from t equals 0 through to 4 seconds, it travels 8 meters. From 4 to 0 and from 0 to -4, it goes from 4 meters to the right of the origin to being at the origin, and then it ends up at 4 meters to the left of the origin at time is 4 seconds. And then from time equals 4 seconds to 8 seconds, it travels from 4 meters to the left of the origin up to 4 meters to the right. It travels another 8 meters. So therefore, in the first 20 seconds, it goes, so it travels 8 lots of 5, 8 times 5, which is, or 5 lots of 8, which is 40 meters, because it goes 8, 16, so it goes 8, another 8, 8, 8, and now we're up to 16 and back down for another 8, yeah, for those remaining seconds, because we've got 4 seconds, 8 seconds, 12, 16, 20 seconds, 5 lots of 8 meters. Now the average speed. Now average speed, it's not velocity, it's speed. Speed is the distance travelled over the time, whereas velocity is different. Average velocity is different. you must use the displacement during that time over the time. So we're not doing average velocity, we want average speed. So it's the distance travelled, which is 40 metres in those first 20 seconds. Therefore, it's 2 metres per second. The velocity would actually be quite different. I will do it. If it starts here, it goes down there. That's 4 seconds, 8 seconds, 12, 16, 20. The actual displacement is final position minus initial. It actually ends up at -4. So it's -4 minus 4. It's actually -8 over 20. So the actual displacement is final position minus initial position, which is -4 minus 4, which is -8 over 20. Now that's 4/5 or 0.4. Sorry, no, not 0.4. It's 4/10. Yeah, it is 0.4. It's 2/5 meters per second, and it's -0.4 meters per second. So average velocity is very different to average speed. Average speed, you need the total distance traveled and divide it by the time. Whereas displacement, remember, displacement is just final position minus initial position. And in this case, its final position is at -4 and its initial position was 4. So it's -8 is the displacement. Okay, now for part D, it says show by substitution that x equals 2 and t equals 1 1/3. Sorry, when t equals 1 1/3 and t equals 6 2/3. So I'm going to substitute 2 for x. So 2 equals 4 cos pi on 4t. So we know that x, remember this comes from x equals 4 cos pi on 4t. It says show by substitution that x equals 2 when t is 1 1/3 and 6 2/3. Actually, they just want you to substitute. They don't want you to solve. I mean, we can solve it if we want, but they don't want you solving it. They just want you to substitute t is 1 1/3 to get x is 2. But actually, I'm going to solve it. What they want you to do, they want you to just go sub t equals 1 1/3, and you'll get x equals, just over here, x is 4 cos pi on 4 times, now 1 1/3 is 4 on 3, times 4 on 3, and you'd get 4 cos pi on 3, which is 4 times a half, which is 2. So therefore, when t is 1 1/3, x is 2. And also, if you substitute t is 6 2/3, which is 20 over 3, we get x is 4 cos pi on 4 times 20 over 3. That's cos of 5 pi on 3. 4 times cos of 5 pi on 3, which is quadrant 4, acute angle 60 degrees. So again, it's 4 times a half, which is 2. Now, if you weren't asked to do it that way, and they might ask you to find the times when x is 2, you would substitute x is 2 there, divide by 4, and we'd get 2 divided by 4, which is a half, equals cos of pi on 4t. Now we use our 4 quadrants. Cos of what is a half? So our acute angle pi on 4t is cos of 60 is a half, so that's pi on 3. And we know that we're in quadrants 1 and 4. And so therefore pi on 4t is just this pi on 3, and if that angle there is pi on 3, then this angle here is quadrant 4, so that's 5 pi on 3. And so therefore t is dividing by pi on 4, or multiplying by 4 on pi. We get pi on 3 times 4 on pi, and 5 pi on 3 times 4 on pi gives us, the pi's cancel, time is 4 on 3, and time is 20 on 3, which is what they were asking you to substitute there. Time is 6 2/3, and time is 1 1/3. So that's just solving it if they didn't give you those times, okay? So it says show by substitution that x is 2 when those times occur. Hence use the graph to find when x is less than 2 in the first 8 seconds. Here is our graph of x equals 4 cos. This is the graph of x equals 4 cos pi on 4t. Remember, it's got the period equal to 8 seconds because it was 2 pi divided by pi on 4. Now, when this is amplitude is 4, so x is 2 at these points. Now, what I'm going to do is draw a dotted line here where x is 2, and we know that when time is 1 1/3, all right, this is probably not the best diagram. I should, it's not drawn to scale very well. I could draw it a bit better. And if I go more like this, I don't know if that's any better, but sort of there. That when time is 1 1/3, x was 2. Remember, we did the substitutions of time is 1/3. See here, this is point is time is 2. This here, the point is time is 1 1/3. And here, time was 6 2/3 seconds. Okay, so we can see that when time is a bit over 6 2/3, that x is 2, and when time is 1 1/3, we get that x is 2 as well at this point here. Now, okay, so and it says hence use the graph to find when is x less than 2 in the first 8 seconds. So here is x equals 2. Up here is when x is greater than 2. Up there is when x is greater than 2. But between, so x is less than 2 when the time is between 1 1/3 and 6 2/3 seconds. Okay? So x is less than 2 between 1 1/3 and 6 2/3 seconds. Then it says when during the first 8 seconds is velocity equal to pi on 2 and velocity greater than pi on 2. Now, we need to do the same thing with our velocity curve, okay? So, velocity equals, we need to look at that equation again from the page before. When during the first 8 seconds is the velocity equal to pi on 2? Well, I'm going to sub velocity equal to pi on 2 and get pi on 2 equals negative pi sine pi on 4t. I'm going to do this by solving. Dividing by negative pi, I get negative 1/2 equals sine pi on 4t. Now, this is quadrants 2 and 3, and my acute angle pi on 4t is sine of what is 1/2? It's sine of 30, which is pi on 6. So acute angle pi on 4t is pi on 6. Remember, we're quadrants 2 and 4, so it's pi minus pi on 6. So therefore pi on 4t, actually I'll do it over here. So therefore pi on 4t equals pi minus, if that's pi, that's 5 pi on 6 up to that line, and that would be 7 pi on 6. Okay, and so therefore t is dividing by pi on 4, which is multiplying by 4 on pi. You get 5 pi on 6 times 4 on pi, and 7 pi on 6 times 4 on pi. So the times are, we get 20 on 6, which is 10 on 3, which is 3 1/3. The pi's cancel. And we get, that's a 3, that's a 2, 14 on 3, which is 4 2/3 seconds. So therefore, at time is 3 1/3 and 4 2/3 seconds, we get that the velocity equals pi on 2. Something wrong here, because if I sketch the curve of velocity equals negative pi sine pi on 4t, it looks like that. And if I put pi on 2 and put a dotted line across here, I can see that I've got something bigger than 4 and less than 8 as my times when velocity is pi on 2. So there is an error in this working somewhere which we need to find. My mistake, sorry, a bit late at night, making silly mistakes. Sine is negative in quadrants 3 and 4, not 2 and 3. So I need to come back to quadrant 3 and 4. Sorry about that. Hopefully you've picked that up. I'm not really going to go back and redo that. All right, so hopefully you've seen what I've done wrong. Picked it up earlier. So we've got 7 pi on 6, and this will be 11 pi on 6. So we've got 7 pi on 6 times that. We get 3 and 2, 14 on 3. That was 4 2/3. And this is 11 pi on 6 times 4 on pi. We get 3 and 2, 22 on 3. That's 7 1/3 seconds. So therefore that does actually tie up. It looks right now, because we can see there are 2 times that are between 4 and 8 seconds, and both of these are. I'm really sorry about that there. Just a bit late and making silly errors. Okay, so which is a reason why you should always check your answer and make sure that it seems okay. You would have had that sketch on the page before, and pi on 2, you can see your answers have to be between 4 and 8 seconds. So actually wasn't such a bad thing making that error. Okay, now when is the velocity greater than pi on 2? Well, that velocity is greater than pi on 2 for the values there between 4 2/3 and 7 1/3. So therefore, velocity is greater than pi on 2 when the time lies between 4 2/3 and 7 1/3 seconds. Okay. Question 14, it says a particle is oscillating on a spring so that its height is x equals 6 sine 2t centimeters at time t seconds. You have to find v and acceleration as a function of t and sketch those graphs. Well, the first graph I'll do over here is the sine curve. It's got an amplitude of 6. That's the displacement. Down here's -6, and the period is 2 pi over 2, which is pi, and we want to sketch the graph from 0 actually to 2 pi seconds, which is why you should really read the question before you start drawing, like me. So I'll just redraw that. I've just sort of run out of a bit of room there. So I want a sine curve, +1, 1. I'll just put my period somewhere else. Okay. And do another one of these. It is a bit messy actually. So this is pi and this is 2 pi because the period is pi. Okay, that's a very bad sine curve. Velocity is the derivative of that, which is 6 times cos 2t times 2. So the velocity is 12 cos 2t. So we can draw the velocity curve down here. It's a cos curve. It'll have the same period again of pi, and that would be 2 pi, and that's 12 and -12. This is a velocity curve, and now the acceleration is the derivative of that again, which is 12 times -sine 2t times 2, which is -24 sine 2t. That's the acceleration. So drawing an acceleration curve, it's a negative sine curve, so it'll look like this. I just need to get on screen. That's one period, sorry, one cycle, or one, 2. 2 pi is the period. Pi is the period. We've got 2 periods there. Okay, and the amplitude's 24. And there's your -24 down there. So that's part A. So find V and A as acceleration as a function of t. Sketch the graphs from 0 to 2 pi. And part B says to show that acceleration equals -4x. Now look, this is sort of moving into a simple harmonic motion a bit, but what we'll do, so we know that acceleration, we'll just continue from where we were. We know that acceleration equals -24 sine 2t, which is in terms of, remember, x is 6 sine 2t, so it would be negative 4 times 6 sine 2t. That's what acceleration is, which is, acceleration therefore is negative 4 times x, which is negative 4x. So acceleration is negative 4x. Now part C asks, when during the first pi seconds is the particle at the origin? Well, particle at the origin is at the origin at 0, pi on 2 and pi seconds. So they just want the first pi seconds. So it is at x equals 0 when the time is 0, pi on 2 and pi. When in the first pi seconds is the particle stationary. So it's at rest or stationary, which is v equals 0, when time is, now we've got pi there, that's pi and 2, this is pi and 4, and that's 3 pi and 4. So it will be at rest when velocity is 0 at pi on 4 and 3 pi on 4 seconds. Okay, and the next part is, when is acceleration equal to 0? So we just look at our acceleration graph, which is this last one, and acceleration is 0 at time is 0, pi on 2 and pi seconds. Okay, that's part C. Now part D, when during the first pi seconds is the particle below the origin. Below the origin is when x is negative, so it's between pi on 2 and pi. So they just want to know for the first pi on seconds when it's below the origin. So x is less than 0, particles below the origin, when t lies between pi on 2 and pi. Part 1. Part 2, when is the particle moving downwards? That's when velocity is negative. We can see velocity is negative between pi on 4 and 3 pi on 4 seconds. So moving downwards means is or equals is when velocity is less than 0, and that's when the time lies between pi on 4 and 3 pi on 4 seconds. Okay, and the other one, this was for particle below the origin. That's when particles below the origin. And for part 3, when is the particle accelerating downwards? That's when acceleration is less than 0, and that's between 0 and pi on 2 seconds. So when t lies between 0 and pi on 2 seconds. Okay, now, so these are mainly interpreting the graph, okay? And I think that was part D, yes. Now for part E, find the first time the particle has a displacement of x equals 3. So displacement x equals 3 would be here, and that's the first time when the displacement is x equals 3. And we know it's got to lie, if this is pi on 2, this here, the peak's pi on 4, it's before pi on 4 seconds. So we know that x equals 6 sine 2t. So we're going to substitute x equals 3 into x equals 6 sine 2t, and we get 3 equals 6 sine 2t. Then 3 over 6 is a half, equals sine 2t. Now these are quadrants 1 and 2, where sine is positive, and the acute angle 2t is, we know sine of 30 is a half, so it's 30, which is pi on 6, and therefore 2t, your two angles, which are quadrants 1 and 2, are pi on 6. So we draw pi on 6, and this one here, quadrant 2, that would be 5 pi on 6, okay, because all the way there's pi. So therefore t dividing by 2 is pi on 12, and 5 pi on 12 seconds. but we only want the first time when displacement is x is 3. So therefore, it's at time equals pi on 12 seconds is the first time. So first time that x equals 3 is when time equals pi on 12 seconds. And you can see that would be about the case there. That's pi on 4. So this would be at pi on 12. Okay. Now, the next bit, when does velocity equal 6? Okay, now it's pi on 4. This isn't the best curve, okay? Should really be looking more like that, okay? Now, velocity at time pi on 4 is 0. So at pi on 4, velocity is 0. So we're expecting it before pi on 4 seconds as well. So we're going to substitute v equals 6 into the velocity equation, which is v equals 12 cos 2t. And we get that 6 equals 12 cos 2t. In other words, a half equals cos 2t. The acute angle 2t, cos of what is a half? It's cos of 60. So acute angle is pi on 3. We are in quadrants 1 and 4. So therefore 2t is pi on 3, drawing the quadrants. And there's quadrant 4. And that would be 2 pi minus pi on 3. So it's 1 2/3, which is 5 pi on 3. And now dividing by 2, we get time is pi on 6 and 5 pi on 6 seconds. Now, going back and looking at the graph, it needs to be before pi on 4 seconds, which it is. So here's pi on 4 seconds. It is before pi on 4 seconds. So therefore, the first time that velocity equals 6 meters per second is when time equals pi on 6 seconds. Now, okay, and that's I believe it's actually centimeters per second. Okay, and that one was when x is 3 centimeters. And I believe that's the end of this exercise.